Hello. In this lecture, we'll recall the definition of hyperbolic metric spaces in terms of slim and thin triangles, and then we'll introduce the concept of divergence of geodesics. We'll prove that in a hyperbolic metric space, geodesics diverge exponentially. Okay, so let us begin. So we have started with geodesic metric space. A metric space X is said to be geodesic metric space if every 2 points of X can be connected by a geodesic. So what is the meaning of geodesic? So a map alpha from this closed interval 0d dxy to X is a geodesic if alpha 0 is equal to X, alpha of dxy is equal to Y, and distance between alpha s alpha t is equal to mod of s minus t. We have defined slim triangles. So let us take a non-negative number delta. A triangle delta xyz in a metric space is said to be delta slim if each side of delta xyz is contained in closed delta neighborhood of union of other two sides of the triangle delta xyz. So this already we have seen. And what is the meaning of thin triangle? So let us take a non-negative number delta. A triangle delta xyz is said to be delta thin. So if there exist points Cx, Cy, Cz such that Cx belongs to Yz, Cy belongs to Zx, and Cz it belongs to Xy, such that the following holds. So distance between Xcy is equal to distance Xcz, distance between Ycx is equal to distance between Ycz, and distance between Zcx is equal to distance between Zcy. And if Yt belongs to this geodesic joining Xcy and Zt belongs to the geodesic joining Xcz, such that distance between xyt is equal to distance between xzt. So then distance between yt zt is less than equals to delta. And similarly for the other sides also. So if xt belongs to the geodesic joining ycx, zt belongs to the geodesic joining ycz, such that distance yxt is equal to distance yzt. So then distance between xt zt is less than equals to delta. And if xt belongs to the geodesic joining zcx, yt belongs to the geodesic joining zcy, such that distance between zxt is equal to distance between zyt. So then distance between xt yt is less than equals to delta. So this thing we have done in the previous class, and we have also proved this theorem. So a triangle is thin implies that it is also slim. So if I take a triangle to be delta thin, so then it will be also delta slim. So this part is easy. And the converse is true in this following way. So in a metric space, if all triangles are delta slim, so then there exists a delta prime depending on this delta such that triangles are delta prime thin. And what is the definition of hyperbolic metric space? So a geodesic metric space is said to be delta hyperbolic metric space if all triangles are delta slim. So this means that there exists delta prime such that all the triangles are delta prime thin in a delta hyperbolic metric space. So these examples already we have seen. So if I take this upper half plane with hyperbolic metric, so this is log 3 hyperbolic metric space. A tree is a 0 hyperbolic metric space. And this thing will see it later. So this third example will see it later. If I take SG to be a closed orientable surface of genus G, where this G is greater than equals to 2, so then the fundamental group of this genus G surface is a hyperbolic metric space. So this will prove later. And now let me come to the definition of this divergence function. So we say a function E from r greater than equals to 0 to r is a divergence function for a metric space X if for all points X in this metric space and all geodesics gamma from X to Y and gamma from X to Z. So the function E satisfies the following. So for all capital R and small r belonging to r greater than equals to 0, such that capital R plus small r is less than the minimum of length of the geodesic xy and length of the geodesic joining x and z. And if we assume this distance between this gamma r and gamma prime r to be greater than 0, and if alpha is a path lying in the closure of the complement of this ball. So you take the complement of this ball around x of radius r plus capital R plus small r, and you take the closure. So alpha lies here. So alpha is a path lying in the space joining these 2 points gamma r plus small r and gamma prime r plus small r. So then length of alpha is greater than E of r. Yeah, so let me draw a picture. So this is my point X. And we have two geodesics emerging from the point X. So this geodesic, I have called it to be gamma, and this geodesic, I have called it to be gamma prime. So gamma r, so it will be a point on this geodesic, and gamma prime r, it is a point on this geodesic. So distance between x gamma r is equal to r, which is again equal to distance between x gamma prime r. And now what we have done, so we have taken points gamma r plus small r on this geodesics. And now what you do, so you take a ball of radius capital R plus small r with center x. So this is my ball. And now what you do, so you take a path alpha lying outside the ball. So this alpha, it is a path in the closure of the complement of this ball. So we say E to be divergence function. So also we have assumed this thing, distance between gamma r and gamma prime r is greater than E0. So E is said to be divergence function if length of alpha, it is greater than E of r. Yeah. So what we are going to prove that, so this function E, it is exponential if X is a delta hyperbolic metric space. Okay. So if for a metric space X, so there exists a divergence function E, which is exponential. So then we say geodesics in X diverge exponentially. Okay. So this is my theorem. So in a hyperbolic metric space, geodesics diverge exponentially. So we need to find a divergence function which is exponential. Okay, let us see how to prove it. So let us take two geodesics, gamma from x to y and gamma from x to z, uh, in a delta hyperbolic metric space X. So because X is a delta hyperbolic metric space, so we can assume that triangles are delta thin. And now suppose we take two non-negative numbers, capital R and small r, such that distance between this gamma r and gamma prime r is greater than 2 delta plus 1. So we have this two geodesics here. So we have this two geodesics here, and this distance, so this distance is greater than 2 delta plus 1. So let us assume that thing. And also we assume that capital R plus small r is less than minimum of length of xy and length of xz. And now we take this gamma r plus r, so this will be a point on this xy, and gamma prime r plus r, so this will be a point on xz. And now let us take alpha to be a path. So alpha to be a path in the closure of the complement of this ball of radius capital R plus small r around x, connecting this gamma r plus r and gamma prime r plus r. Okay. And now what we are going to do, so let us join this gamma r plus small r and gamma prime r plus small r by a geodesic of X. So here we are assuming this X to be a geodesic metric space. Okay. So now let us think of this triangle. So consider this triangle. So this triangle. So which is delta thin, we know. Okay. So now, because this 2 points lie at a at lie at least 2 delta plus 1 distance apart. So therefore, so for this point, so there exist points here so there exist points P on this geodesic joining gamma r plus r and gamma prime r plus r such that this distance is less than equals to delta. So this distance is less than equals to delta. So if length of alpha is less than equals to 1, then because this is a geodesic, its length will be also at most 1. So hence the distance between P and P prime, that will be also less than equals to 1. So therefore distance between gamma r and gamma prime r, so that will be less than equals to 2 delta plus 1. So if this distance is less than equals to 1, so then distance between gamma r and gamma prime r will be less than equals to 2 delta plus 1. So that is a contradiction to this thing. So therefore, so length of alpha, it cannot be less than equals to 1. So length of alpha is always greater than 1. So that's why we have taken this distance between gamma r and gamma prime r to be greater than 2 delta plus 1. Okay, so now, so what we are going to do, so we subdivide this alpha in the following way. So first subdivision is the following. So alpha is equal to alpha naught union alpha 1 such that length of alpha naught is equal to length of alpha 1 equal to half of length of alpha. So you divide this alpha in 2 equal parts. So divide this alpha in 2 equal parts. So what you will get? So this is alpha 1 and this is alpha 1. So you'll get a point on alpha such that the length of alpha is equal to length of alpha 1, which is equal to half of the length of alpha. So that thing we have done. And you continue this process. So you take alpha naught. So again you subdivide into 2 equal parts. And also you subdivide this alpha 1 in 2 equal parts. Okay. So you continue this process. So there exists some natural number n such that length of alpha is greater than 2 to the power n minus 1 and it will be less than equals to 2 to the power n. So this will imply that half is less than 1 by 2 to the power n times length of alpha less than equals to 1. Okay. Yeah. So we have divided this this alpha first in 2 equal parts. So then again take each subdivision, divide again in 2 equal parts. You continue this process and you stop at this n. So where half is less than length of alpha divided by 2 to the power n less than equals to 1. Now let us take W to be a word in 0, 1, 1. So for example, alpha can be 0, 0, 1, 0, 1, 0, 0, 0, 1, something like this. So let us take alpha to be a word in 0, 1 of length n. So if n is equal to 3, so 0, 1, 0, it is a word of length 3. 0, 1, 1, it is a word of length 3. So let us take W to be what in 0 and 1 of length n. Okay. So this alpha, so this will be union of this alpha u, where this u is a word of length n in 0 and 1. And length of each of this subword, subpart of this alpha, so length of alpha w, so this will be equal to 1 by 2 to the power n times length of alpha. Okay. So now let us take m to be the midpoint of alpha and mw to be the midpoint of alpha w. So note that w is a word of length n. Yeah. So this is my picture here. So this is my alpha. So this is my alpha. And we have taken the midpoint. So this m is the midpoint. m0 is the midpoint of alpha 0, 1. m1 is the midpoint of alpha 1, 0. And you continue this process. Okay, so now what you do, so you join gamma r plus small r and m by a geodesic, and gamma prime r plus small r again by a geodesic. Now take the point m0. So again you join gamma r plus r to m0 by a geodesic. Join m0 to m by a geodesic. Join m to m1 by a geodesic, and gamma prime r plus r to m1 by a geodesic. And you continue this process. Okay, so now we have so many triangles. So first consider this triangle x gamma r plus r, gamma prime r plus r. So again this triangle is delta thin, and because this distance between gamma r and gamma prime r is greater than 2 delta plus 1, so for this gamma r, so there will exist a point on this geodesic such that so that point I'll take it to be b0, b0, such that distance between gamma r and this point is less than equals to delta. So again you take this triangle. So now you take this triangle gamma r plus r, gamma prime r plus r, m. So this triangle. So there will exist a point b1. So there will exist a point b1 in the union of these two sides such that distance between b0 and b1 will be less than equals to delta. So in the picture, so this b1 is this point. So this is my point b1. So this distance, so this is less than equals to delta. So now you take this triangle. So suppose b1 lie in the geodesic gamma r plus r m. So then you take this triangle, and for this b1, so again you'll get a point either on this geodesic joining gamma r plus r to m0, or m0, or on the geodesic m0 to m, such that distance between V1 to that point is less than equals to delta. So let us take that point to be V2. And let us take this V2 to be on the geodesic joining M and M naught. Yeah, so that thing I have written it here. So if P1 belongs to this geodesic, there exists P2 belongs to union of these two geodesics, such that distance between P1 and P2 will be less than equals to delta. Okay, so now we continue this process till n steps. Now note that, so distance between Vi and Vi plus 1 will be less than equals to delta. And at the nth step, so distance between Vn and alpha will be less than equals to 1, because length of each alpha w is at most 1. So length of alpha w, it is equal to length of alpha by 2 to the power n. So that is less than equals to 1. Okay. So now what is the distance from x to the path alpha? So that will be less than equals to, just now you just apply this triangle inequality. So distance from x to this path alpha. So what is this? So that will be less than equals to distance from x to gamma r, that is this distance plus this distance plus this distance. Okay, so distance x to gamma r plus distance gamma r to V0. So plus dot dot plus distance Vi to Vi plus 1 and up to distance Vn to alpha. So the first one, because gamma r it is a geodesic, so this will be equal to r. And we have n plus 1 terms here up to this thing. So it will be n plus 1 terms, and each one of them is less than equals to delta. So we have n plus 1 times delta plus 1. So this distance is less than equals to 1. And also observe that, so because alpha lies outside the ball of radius capital R plus small r around x, so distance between x and alpha will be greater than equals to capital R plus small r. So therefore, so by these two inequalities, so what we have, capital R plus small r is less than equals to this thing. And again note that 2 to the power n minus 1 is less than length of alpha less than equals to 2 to the power n. So this implies that if I take log base 2, so log of length of alpha, that is less than equals to n, less than log length of alpha plus 1. Yeah, so now from this equation start, so what we have, small r is less than equals to n plus 1 times delta plus 1. And now from this inequality, so what we have, so this one will be less than log length of alpha plus 2 times delta plus 1. And so eventually what we'll get, length of alpha is greater than 2 to the power r minus 1 by delta plus 1 minus 2. So now we define this function e from r greater than equals to 0 to r by the following way. So e of r, so this is maximum of 2 delta plus 1 and 2 to the power r minus 1 by delta plus 1 minus 2. So this e, it is a divergence function, and because of this, it is an exponential divergence function. So therefore, what we have proved that geodesics in hyperbolic metric space diverge exponentially. So in the next lecture, we'll prove that if geodesics diverge exponentially in a geodesic metric space, so then that metric space will be a hyperbolic metric space. Okay, I'll stop here.